In today's class, we will discuss about no-load and block rotor test on three-phase induction motor. So this no-load and block rotor test on three-phase induction motor, it is very similar to the open circuit OC test and short circuit SC test, whatever we have studied for transformers. Okay. So no load test means you should not connect the load to the induction motor and apply the rated voltage and note down V naught, I naught, W naught. And for the short circuit test or the block rotor test, you should hold the rotor till rated current flows through the ammeter and note down corresponding short circuit voltage VSC, corresponding short circuit current ISC, and armature, then copper loss information using the wattmeters, that is 2 wattmeter method. uh, so that is nothing but WAC. Okay, so now this no load and block rotor test on induction motor, it is the experiment used to determine the performance of three-phase induction motor, and this experiment information it is required to draw the circle diagram, where circle diagram it is the graphical method to estimate the performance characteristics of three-phase induction motor, where using this circle diagram graphical approach method you can find out different what is that performance characteristics of three-phase induction motor, like slip, torque, input, output, efficiency. So all the performance related parameters of three-phase induction motor can be calculated using circle diagram, and to draw the circle diagram you should have the information of no load and block rotor test experiment on three-phase induction motor. Okay, now let us see the description for no load and block rotor test on three-phase induction motor. This is also one of the important question which will be asked in the VTU final exam. Okay, now let us see the explanation for this. The data required to draw the circle diagram is obtained by two tests, which are first one no load test or the open circuit test, second one block rotor test or short circuit test. Okay, now let us see the in detail description for no load and block rotor test. Coming to the first one, that this is no load test. So circuit diagram for the no load test is this one, where this is the stator of the three-phase induction motor, this is the shaft, and this is wattmeter W1, this is wattmeter W2, this is ammeter, then this is the voltmeter connected between two lines here. Okay, so this is a circuit diagram for no load test. Now in the no load test, the motor is made to run without any load. So as the title suggests, here we are not going to connect any load. So it is as good as no load condition. Okay. The speed of the motor is very close to the synchronous speed, but less than the synchronous speed. So here we should maintain the speed very close to the synchronous speed, but it should be very less than synchronous speed. So for example, if synchronous speed is 1500, you can make the machine to run up to 1495. Likewise, it should be very close to the synchronous speed, but it should not be equal to synchronous speed. Okay, then the rated voltage is applied to the stator, the input line current and total input power is measured. So here, keeping the induction motor on no load condition, we should give the power supply to the stator till it should carry the rated voltage. So while it is going to have the rated voltage, then that rated voltage can be read using the voltmeter, and this reading will be no load voltage V naught, then corresponding no load current will be I naught, and corresponding power consumed, that will be the sum of the two wattmeters using the 2 wattmeter method, that is sum of W1 plus W2 gives us no load power. Okay, that is nothing but W naught is equal to W1 plus W2. Now the circuit diagram for the test is shown in figure 4.8.1. So this is the figure 4.8.1 representing no load test, where the stator it is excited with three-phase power supply 440 volts, and it is free from the load. It is no load condition, and it will be having ammeter, voltmeter and wattmeter to measure the different parameters like voltage, current and power. Okay, now as the motor is on no load, the power factor is very low, which is less than 0.5, and one of the two wattmeter is negative. So here, since it is no load condition, and we know that whenever we don't connect any load, then certainly there will be low power factor which will be less than 0.5. Because of that, out of the two wattmeters W1 and W2, one of the wattmeter will be reading negative. Okay, now it is necessary to reverse the current coil or potential coil or pressure coil of such a wattmeter to get the positive reading. Out of the two wattmeters, whichever the wattmeter is reading negative reading, so such wattmeters potential coil or current coil, it has to be reversed. By reversing, it will show the positive reading, but that positive reading, even though it is showing positive, but we should take it as negative reading, okay, like what we do in the laboratory. This reading must be taken negative for the further calculations. So I told you, so whichever watt meters potential or pressure current coil we have reversed, that reading we should take it as negative reading, okay. Now the total power input W naught is the algebraic sum of the two wattmeter readings the observation table is. So after applying the rated voltage which is observed using V naught, then we should note down the different readings. So now the total power consumed is nothing but sum of algebraic sum of W1 plus W2. Okay. Now this is the observation table for no load test, where we are going to note down different parameters like V naught voltage, that is rated line voltage, I naught ampere, that is no load current, then W naught is equal to W1 plus W2. So which is nothing but the algebraic sum. So this is no load voltage V naught. This you have to note it down here. Then this is a no load current. This you have to note it down here. Then W1 plus W2 is nothing but the algebraic sum of the two wattmeters. Okay, now let us see the calculation part from these readings. So the calculations are no load power W naught. This is also given by the formula three phase power supply. That is nothing but root 3 V naught I naught cos pi naught, where the cos pi naught is nothing but what? No load power factor. From this we can write W naught is equal to, sorry, cos pi naught is equal to numerator part W naught upon denominator root 3 V naught I naught, where V naught I naught are line values. So this is the no load line voltage and this is the no load line current. Okay. Now this is no load power factor, means this cos pi naught is nothing but the no load power factor. Okay. Thus we are now in a position to obtain magnitude and phase angle of no load current I naught, which is required for the circle diagram. So while plotting the circle diagram, initially we need to draw the current phasor I naught, and to plot that current phasor I naught, we are in the requirement to have the information related to the magnitude and phase angle of I naught. So to get that information, we are going to make use of this cos pi naught. Okay. Now from the knowledge of no load current I naught and no load power factor angle pi naught, the parameters of the equivalent circuit can be obtained as. So after once we calculate this cos pi naught, I naught, V naught, everything, using this now we will be calculating different parameters related to the magnetizing branch of the equivalent circuit of three phase induction motor. So they are active component of the no load current, that is nothing but what? IC. So IC is given by the formula I naught cos pi naught, where I naught is the no load current and cos pi naught is the no load power factor. Similarly, the magnetizing component of no load current denoted by Im, this is given by the formula I naught sin pi naught. So these formulas are very similar to the formulas related to the equivalent circuit of three phase induction motor. Then followed by that, no load magnetizing branch resistance R naught is given by the formula V naught per phase divided by IC per phase. That is nothing but the no load branch resistance. Then after that, no load reactance, magnetizing branch no load reactance X naught is equal to V naught by I naught per phase, that is nothing but no load branch reactance. So all these are the parameters related to the magnetizing branch, that is IC, Im, R naught, X naught, where IC is given by I naught cos pi naught, Im is given by I naught sin pi naught, R naught is nothing but V naught by IC, X naught equal to V naught by Im. So all these formulas are very familiar to you, which we have already seen for equivalent circuit of transformer. So whatever transformers formulas they are there, the same will be there even for the induction motor also. Now the power input W naught consists of following losses. So now, as we have seen here, W naught is nothing but what? It is the algebraic sum of two wattmeters, that is W1 plus W2. Now let us see this W naught. It is the information related to which all parameters. Okay. Now the power input W naught consists of following losses. The first one is stator copper loss, that is 3 I naught square R1, where I naught is no load per phase current and R1 is stator resistance per phase. So W naught, it is having the information related to the stator copper loss, and also it is having the information related to the stator core loss, that is nothing but iron loss. Then it is having friction and windage loss, that is nothing but the mechanical losses. So altogether this W naught gives us the information related to the stator copper loss, stator iron loss, friction and windage losses. Now let us see rest of the things. The no load current is very small and hence rotor copper loss is negligibly small. Yes or no? Because here, since we are not connecting any load, so no load current will be very small. If no load current is very small, then obviously copper loss will be very small. Because of that, we can neglect the rotor copper loss. Okay. Now, the rotor frequency is a S times supply frequency. Also, we know that in during running condition, rotor frequency will be slip times of the supply frequency, which is very small, and on no load it is very small. Okay. Now, rotor iron losses are proportional to this frequency and hence are negligibly small. Also, we know that rotor iron losses, they are dependent on frequency. Since rotor frequency is small, then automatically rotor iron losses will be very small. Okay. Now, under no load condition, I naught is very small, and in many practical cases it also neglected. So since no load current means you are not connecting any load, so no load current I naught will be very small, and hence it can be neglected in many of the cases. Thus W naught, that is no load power W naught, consists of stator iron loss and friction windage loss, which consists for all the loading conditions. So whatever may be the loading condition, so W naught, it indicates the information related to the stator iron loss, friction and windage losses. Okay. Hence, W naught is said to give fixed losses of the motor. Okay, so because this iron loss, this W naught, which is nothing but the no load loss, this gives us the information related to the fixed losses. Fixed losses is nothing but the constant loss, where in the case of induction motor, constant loss, it is a sum of iron and mechanical losses. That is, mechanical losses means friction and windage losses. Okay, so therefore, finally, W naught is nothing but this is the information related to the no load power. That is nothing but W naught is equal to fixed losses, where neglecting stator copper loss, because since it is no load current, because of that copper losses will be very small in the case of stator part. Because of that, we finally conclude that W naught is having the information only related to the fixed loss. Fixed loss means iron plus friction and windage loss, which is nothing but mechanical loss. Now after this, how to separate the no load losses, let us see here. Separating the no load losses. So this is the graph where this is the power during no load condition along y-axis, and along x-axis this is the rated voltage. Now the no load losses are the constant losses, which include core loss and friction and windage losses. We know that no load or the fixed losses, it is a sum of core loss, friction and windage loss. Okay. Now we are going to separate core and friction windage losses. The separation between the two can be carried out by no load test conducted from variable voltage, rated supply frequency. So how to separate the fixed losses? Fixed losses, it is a sum of iron and friction windage losses. So now we are going to separate the iron and friction windage losses, and that too during no load condition, by applying the variable voltage here, but keeping the supply frequency constant, because stator will be supplied with constant frequency supply. Okay. When the voltage is decreased below the rated value, the core losses reduces as square of the voltage. So here when we decrease the voltage below the rated value during for the no load test, then the iron or the core losses, it also starts to reduce nearly square of the voltage. Okay. Then what happens, as we keep on decreasing the voltage, slip does not increase significantly. The friction and windage losses almost remains constant. So after this, slip will not vary significantly, it is almost trying to remain constant, and along with that, friction and windage losses, they are also going to remain constant. Okay. Now the voltage is continuously decreased till the machine slip suddenly begins to increase and the motor tends to stall. Means here initially no load test, it is conducted for rated voltage. After that, what we should do, we should keep on decrease the voltage. How long we should decrease the voltage means slip should increase. When the slip increases, when machine comes to the resting condition, slip will be maximum, that is slip S is equal to 1. So we should keep on decreasing the voltage till slip increases and machine comes to the resting condition. I mean to say here is that machine should come to the standstill condition. So during standstill condition, slip will be increasing, that is slip will be maximum, that is S equal to 1. Okay. Now at no load, this takes place at a at no load condition, this takes place at a sufficiently reduced voltage. So now you should if this is the point where this is for rated voltage, now you should keep on decreasing the voltage till the machine should come to the resting condition, till it should come to the resting condition. So here I can say that it has come to the resting condition. So rated, this is the rated voltage, and here we are keep on decreasing the rated voltage till the machine is coming to the resting condition. So this is the point where machine has come attained to the resting condition. Now after this, let us see now. At no load, this takes place at a sufficiently reduced voltage. The graph showing no load power no load losses versus variable voltage V as shown in the figure 4.8.2. So this is the graph between no load power along y-axis and along x-axis. This is the rated voltage. So this rated voltage, it is this point, and as we keep on decreasing the voltage, then machine will be trying to increase the slip and it will come to the standstill or resting condition. This is the resting condition point. Okay, now after this, the from the figure 4.8.2 is extrapolated to voltage V equal to 0, which gives friction and windage loss as well as iron or core loss is 0 at 0 voltage. So now once you get the what is that resting condition point, that is this voltage point, further you should take the extrapolation for this voltage point such that it should reach to the 0 voltage point. So once if you take the extension or the extrapolation as it touches to the y-axis, so now this much portion, it is the information related to the friction and windage losses, and rest of this much portion, so out of this total axis, so this much whole portion is the core and iron losses. This is core or the iron loss, and rest of the things from this point to this point, this will be the friction and windage losses. So this is how we can separate the fixed loss is, it is a sum of core and friction windage loss. So if you want to separate those things, then you should keep on decreasing the voltage till machine should come to the resting condition where S will be equal to maximum, that is S will be equal to 1. And once you attend to this point, further you should take the extrapolation till it should touch to the y-axis. Now wherever it is going to touch to the y-axis, then this much portion from this point to this point, it will be friction or windage losses, that is nothing but the mechanical loss, and rest of the things from this point to other point, this will be the iron or the core losses. So altogether core plus friction windage loss, this will be the fixed loss, which is given by 2 wattmeters, that is W naught equal to W1 plus W2. So this is how we are going to separate the fixed losses. Okay, fine. Now the voltage is continuously decreased till it is going to give us the what is that extrapolation point, and from there we should trace out the iron and friction windage losses. Okay, after this, now let us move to the second test. So the second test is what? Blocked rotor test. So this block rotor test is nothing but the short circuit test, what we have seen for the transformer. And for the short circuit test, the conditions are what? It should be in the case of transformer secondary, we are shorting and we are making the ammeter to carry the rated current. But here in this case, secondary is nothing but the rotor of the induction motor, and here we should hold the rotor till ammeter which is connected to the circuit in the block rotor test, it should carry the rated current. Once it is allowed to carry the rated current, then we should note down the corresponding voltage, current and power readings. Okay, now let us see the explanation for this. In block rotor test, the rotor is locked. Locked means we are going to block it or we are going to hold it tightly, what we see in the laboratory. Okay, and then and it is allowed to and it is not allowed to rotate. So here we are going to hold the rotor tightly and it is not allowed to rotate. Thus the slip will be, if it is not rotating, means what? It is at the standstill condition, and we know that during standstill condition slip S will be equal to 1, and the mechanical load reflected to the RL dash is nothing but the mechanical load, and this mechanical load RL dash is nothing but mechanical load reflected to the stator side. RL dash is equal to R2 dash into 1 minus S upon S is 0, because here we have holded the rotor, means mechanical load will also be 0. It is not carrying any load here. If the motor is slip ring induction motor, then the windings are short circuited at the slip ring. So suppose if the induction motor is squirrel cage, then we can hold the rotor, but if it is slip ring induction motor, then we should short the slip rings. Okay, now in order to carry the block rotor test. Okay, the situation is exactly similar to the short circuit test on transformer. As I told you, it is very similar to the short circuit test on transformer. If under short circuit condition, if primary is excited with rated voltage, a large short circuit current can flow, which is dangerous from the windings point of view. We also know that the other name for the short circuit test is reduced voltage test. Here we are going to apply very small amount of the voltage, only that much voltage is sufficient to carry the rated current. Okay, so here since it is a short circuit test, so here we should not allow rated voltage. Okay, so if we allow the rated voltage during short circuit condition, it may damage the windings of the induction motor, which is very dangerous. Okay, so similar to the transformer short circuit test, the reduced voltage about 10 to 15% of the 10 to 15% of rated voltage is just enough, such that stator carries rated current is applied. So here, suppose if the rated voltage is 440 volts, so 10 to 15% of the 440, it means that 40 to 60 volts is sufficient enough to carry the rated current for the induction motor during block rotor test. Because of this only we say rotor, what is that, block rotor test or short circuit test as reduced voltage test. Okay, so for this block rotor test, very small amount of voltage we are injecting just to allow the induction motor to carry the rated current. Okay, now the applied voltage VSC, the input power WSC, and short circuit current ISC are measured once ammeter, once the rotor is blocked, and if we allow induction motor to carry the rated current at that period of time, immediately we should note down the readings of the voltmeter, that is nothing but short circuit voltage VSC, input power, that is nothing but copper loss WSC from the wattmeter, and short circuit current ISC from the ammeter. So these three meter readings we should note it down, which is very similar to the short circuit test of transformer. And now, as mechanical load RL dash is 0, the equivalent circuit is exactly similar to that of transformer, and hence the calculations are very similar to the short circuit test of transformer. Here in this case, we are not going to apply any load on the rotor sides, and so because of that, mechanical load RL dash is 0. If mechanical load RL dash is 0, means the equivalent circuit of induction motor is very similar to the equivalent circuit of the transformer. Because of that, whatever formulas they are there for the transformer calculation part of SC test, the same will be there even for the block rotor test of three-phase induction motor. So now here in this case, VSC is nothing but the short circuit reduced voltage, line voltage. So here, once you allow the induction motor to carry the rated current at that period of time, whatever this VSC voltage reading will be there, that is nothing but the short circuit reduced voltage, that too it is line voltage value. Then corresponding ISC is nothing but the short circuit current value, this is also line value. Then WSC is nothing but the short circuit input power, WSC is nothing but the short circuit input power. Now these are all the three readings which we are going to note it down from the voltmeter, ammeter, and wattmeter. This WSC is nothing but sum, algebraic sum of W1 plus W2 in the case of block rotor test. And now we also know that copper loss WSC, or input power in the three-phase supply, it is given as W is equal to root 3 VI cos pi. Similar to that, now we will correlate that formula to the block rotor test here. So W is replaced by WSC root 3, V is replaced by VSC, I is replaced by ISC, and cos pi is replaced by pi SC. So altogether, finally we reach to the equation WSC is equal to root 3 VSC ISC cos pi SC, where all the voltage current values are line values. Okay. So now from this I can write short circuit power factor cos pi SC is equal to ratio of WSC upon root 3 VSC ISC. So this is the short circuit power factor. And now thus this gives us short circuit power factor of an induction motor. So now, as I have told you, the no, if the load on the induction motor is 0, that is RL dash is 0, so whatever the equivalent circuit of transformer will be there, the same will be there even for the induction motor also. So now the equivalent circuit is as shown in figure 4.8.3. So this is the equivalent circuit of the three-phase induction motor, which is having equivalent resistance referred to the stator side R1E, equivalent reactance referred to the stator side X1E, and here it is at the resting condition because we are blocking the rotor and not allowing the rotor to move, means it is having speed n equal to 0, slip s equal to 1, and it is not having any mechanical load, so RL dash will be 0, and applied rated voltage, applied short circuit voltage is VSC, and it is allowed to carry the rated short circuit current ISC. So this is the equivalent circuit of three-phase induction motor. So now we also know that copper loss formula. Copper loss is nothing but I square R loss. If it is for three-phase machine, then it will be written as WSC is equal to 3 times of ISC square R1E. So this is nothing but the copper loss. So from this I can write short circuit current ISC is equal to, this is nothing but the per phase value. Already we are known. We are having the information of ISC from the wattmeters, from the ammeter. Okay. So ISC is equal to per phase value. From this expression, I can write what is this? This is the equivalent resistance referred to the stator side R1E. 1 stands for stator, 2 stands for rotor in the case of induction motor. So the rotor resistance, rotor equivalent resistance, induction motor equivalent resistance refer to the stator side. R1e is equal to ratio of WSC by 3 times of ISC square. Okay, and now let us see the uh, next part here. So this is the equivalent resistance referred to the primary means stator side, primary for the transformer, stator for the induction motor. So this is nothing but what? This is the equivalent resistance of the induction motor referred to the stator side. One stands for stator, two stands for rotor in the case of three-phase induction motor. And now Z1 is, so this Z1 is nothing but the equivalent impedance referred to the stator side, and this Z1 is given by the formula short circuit voltage VSC divided by short circuit current ISC. These are already available for us using the voltmeter and ammeter reading from the block rotor test. VSC by ISC, that is short circuit per phase voltage, short circuit per phase current. Then after this, once we know resistance R and impedance Z, then from R1E and Z1E we can calculate the X1E value, where X1 is nothing but the equivalent reactance referred to the stator, and it is given by X1 is equal to square root of Z1E square minus R1E square. So Z1E square minus R1E square. So this is all about the block rotor test calculation, where we are going to get the remaining equivalent parameters of the equivalent circuit, that is R1E, X1E, Z1E we are getting from block rotor test, which is very similar to the short circuit test of transformer, and magnetizing branch parameters like R0, X0, I0, IC, IM, all those things we'll be getting from no load test. So this is very similar to the OC and SC test of transformer, right? And now, during this test, the stator carries rated current, hence the stator copper loss is also dominant. So here we are allowing induction motor stator to carry the rated current. So because of that, induction motor's stator, it is having full load copper loss. Okay. Similarly, the rotor also carries short circuit current to produce dominant rotor copper loss. So here, once stator is allowed to carry the current, means rotor is also going to carry the current because of the mutual induction. Because of that, in the case of rotor also, you will be finding copper losses. So as the voltage is reduced, so for the block rotor test we are applying very short voltage value, so very small voltage value, which is nothing but the reduced voltage test. The iron loss, which is proportional to the voltage, is negligibly small. So since our applied voltage is small in the case of block rotor test, and we know that iron losses, they are dependent on voltage. Since voltage is small, then automatically iron losses will be small. Okay, the motor is at standstill, hence mechanical loss, that is friction and windage losses, are also absent. So since here in this case we are blocking the rotor, where blocking means we are not allowing the rotor to move, so because of that, friction, mechanical loss like friction and windage losses, they will be absent. Hence we can write that WSC, short circuit power, is equal to simply it is stator copper loss plus total rotor copper loss. Totally it is going to carry the information of copper loss related to the stator and rotor part. Okay, so WSC in the case of block rotor test gives the information of copper loss. So copper loss that is taking place in stator part, copper loss that is taking place in rotor part of the induction motor. Okay, now, but it is necessary to obtain short circuit current when normal voltage is applied to the motor. But we want short circuit current when normal voltage is applied. Normal voltage means, suppose if it is three phase machine, means we should apply 440 volts. But if we apply such a 440 volt high voltage, then machine will damage, windings will damage, which we cannot apply it in real time. Okay, this is practically not possible. This is not possible. But the reduced voltage test results can be used to find current ISN, the current ISN, which is short circuit current if normal voltage is applied. So here, since block rotor test is the short circuit test, which is carried out for small amount of voltage, allowing the rated current to flow, but we want the information of the short circuit test or the block rotor test when we apply the rated voltage, but we cannot apply rated voltage during short circuit test, which may damage the machine, right, or induction motor. So that is not possible. But using the results of block rotor test, which are at low voltage value, those information you can use it, and you can convert that to the normal voltage value. Using that, we can calculate the current ISN, where current ISN is nothing but the short circuit current if we apply the normal voltage. So S stands for short circuit, N stands for the normal voltage. ISN is nothing but short circuit current if normal voltage is applied. Okay, now let us see how the calculations can be done here. If VL is the normal rated line voltage, then VSC is the reduced short circuit voltage. This is also line value. VSC is nothing but the short circuit voltage for reduced voltage, which is the reading from which we get it from block rotor test. And now ISN is the short circuit current if we apply the normal rated voltage. This is given by the formula VL by VSC into ISC, where VL is the normal rated line voltage, VSC is the short circuit voltage for reduced voltage, and ISC is the short circuit current for the reduced voltage. For the reduced voltage. So this is how we can calculate the short circuit current if we apply the normal voltage. So this formula is very important while drawing the circle diagram. There we are going to make use of this ISN formula, where ISC is the short circuit current at the reduced voltage. So this ISC is nothing but the short circuit current at reduced voltage, and ISN is nothing but the short circuit current if we apply the normal voltage. Now power input is proportional to the square of the current. So here whatever power you are applying, it is proportional to the square of the current. Now let us calculate the short circuit power if we apply the rated voltage. So WSC is the copper loss for reduced voltage, but we want for normal voltage information. So now convert that short circuit information which is there for reduced voltage to the normal voltage. So now WSN is the short circuit input power at normal voltage, and this can be obtained as WSN is equal to short circuit current at the normal voltage value, that is ISN, divided by short circuit current ISC whole square into WSC, where ISN already we have calculated by the formula VL by VSC into ISC, where once again VL is nothing but the rated line voltage, and VSC is and ISC this will be getting from block rotor test for reduced voltage. So now using this ISN we are going to calculate short circuit power, that too for normal voltage, that is nothing but WSN, that is given by the formula ISN upon ISC whole square into WSC, where ISN is the short circuit current if we apply the normal voltage. This can be calculated using this formula VL by VSC into ISC, whereas WSC is the short circuit power at reduced voltage, ISC is the short circuit current at reduced voltage. So these two informations will be getting it from the block rotor test. Okay. But at normal voltage, core loss cannot be neglected. So if we apply the normal voltage, we cannot neglect the core loss. Why? Because core or the iron losses, they are dependent on the voltage. Okay, so therefore now this WSN is the information related to the normal voltage, means it will be going to have core loss information also, iron loss information also. Therefore WSN now it is going to have core loss plus stator and copper loss. Initially WS, this is nothing but what? WSC. WSC, it is going to give us the information only related to the copper loss belonging to the stator and rotor. But now if we convert the copper loss information to the normal rated voltage value, for the normal rated voltage value it will be having even iron losses also, or the core loss also. Why? Because core loss, it is dependent upon the voltage. Here we have applied 440 volts, means it is going to have iron losses also. Because of that, now the WSN, it is having the information related to the iron losses also, that is nothing but WSN, which is nothing but the short circuit power. If we apply the rated voltage, it is going to have the information of iron losses or the core loss plus stator and rotor copper loss. So this is all about the explanation for block rotor test and no load and block rotor test. So this might be asked in the final VTU exam. The question will be like, with a neat sketch explain no load and block rotor test. So here you can see, discuss the procedure for no load test and block rotor test on a three-phase induction motor. How are the parameters of equivalent circuit are determined from the test results. So this might be the type of question what you may get it from in the final VTU exam, and this will be asked for 10 marks. Okay, so if this is the question which will be asked in the exam, means what you should do is you should explain it from the beginning. You should explain it from the beginning here. So start to explain from this point. From here you need to explain everything whatever I have explained till now. You should explain in detail with all the neat circuit diagram, tabular column, no load formulas, equivalent circuit, magnetizing branch parameters, how you are going to calculate using the no load test information. Then W naught, it is going to have the information of stator, core loss, iron loss, friction windage loss, everything. That is W naught is nothing but totally it is a fixed loss. Then how to separate the fixed loss, that is iron loss and friction windage losses, how you are going to separate it using this no load test. You should explain for the procedure, then you should draw the graph, and after that then you should explain for the block rotor test. then whatever results you will be getting for reduced voltage, their parameters, their notations, its equivalent circuit, formulas. Then finally, you should explain for what will be the parameters for the current and power if you apply the rated voltage during short circuit test, that is block rotor test. So IS and WS and all these formulas you need to explain. So till here you should explain it for the no load and block rotor test if it is asked in the final VT exam. Okay, so this is also one of the important question which will be asked in the final VTU exam.